If you can keep lettuce alive in a sealed space module, you can build a far better setup in your own home. The trick is not the plant. The trick is the environment. Lettuce wants cool roots, steady moisture, and clean airflow. Once you stop forcing it into dirt and start feeding it like a controlled system, the harvest becomes faster, cleaner, and more reliable. Today, you are building a $10 NASA-style lettuce farm where the roots live in air, not in mud. Instead of dropping a seed in the ground and hoping it survives the weather, aerospace agriculture treats cultivation as an engineered process. We isolate the variables and manufacture the exact physical conditions that force the plant to grow. Hyper-efficient growth relies on strict environmental isolation, completely removing the element of biological luck. Traditional potting soil is a chaotic matrix. It retains moisture unpredictably and makes oxygen diffusion highly irregular. Healthy dirt relies entirely on macropores, microscopic air gaps between the particles. But basic physical watering and natural gravity cause compaction, collapsing those gaps over time. This diagram compares aerated soil on the left to compacted soil on the right. When macropores collapse, a physical barrier actively strips oxygen from the root system. The biological result is hypoxia. The roots suffocate inside the dense dirt. Water behaves erratically in this compromised state. It either pools uncomfortably at the surface to create a swamp, or it drains away so fast the lower roots stay entirely dry. To survive, the plant redirects vital metabolic energy just to mechanically push its root tips through the hardened mud. Traditional dirt gardening struggles inherently because soil is physically unstable. To achieve true efficiency, we have to abandon soil entirely and isolate the root zone. To build a superior system, we need to drop the vocabulary of traditional gardening and adopt the strict standards of environmental control. Space agriculture operates on absolute control over mass transfer, the exact rate at which nutrients and oxygen move into the plant's biology. This diagram illustrates the three primary variables that must be localized and controlled for optimal mass transfer: water volume, dissolved oxygen, and light intensity. By manually manipulating these metrics into optimal zones, we force the plant to vastly exceed its natural terrestrial growth rate. The ultimate biological bottleneck for all plant growth is the rhizosphere, the immediate boundary layer surrounding the roots. When you suspend the root system inside a controlled chamber, you perfectly isolate this rhizosphere from external weather, pests, and the chaos of the outdoors. Biological output is directly proportional to the mathematical stability of these inputs. The physical assembly of this $10 system begins with a standard plastic tote. We drill a precise opening directly into the lid. The immediate physical requirement for this container is absolute light deprivation. The sides and top must be wrapped or covered completely. This cross-section demonstrates the biological threat. If light photons penetrate the nutrient reservoir, it triggers aggressive algal blooms across the water. As the algae multiplies, it aggressively consumes all the dissolved oxygen in the water that was meant for the plant. This sudden oxygen depletion drastically shifts the pH of the water, which destroys the delicate root boundary layer. Next, we place a small net pot filled with lightweight clay pebbles into the lid. This holds the seedling's stem securely upright without burying it in a dense medium. The base container functions as a light-proof shield, perfectly isolating the roots from contamination and photons. We fill the lower half of the dark container with an aqueous nutrient solution, deliberately leaving an empty gap between the liquid and the lid. Then we add an active airflow source, like a submerged air stone, in order to continuously and violently agitate the fluid. This diagram details the fluid dynamics. The microbubbles maximize surface area for rapid gas exchange between air and liquid. This continuous exchange maintains maximum dissolved oxygen, biologically preventing root rot and stabilizing the boundary layer. Inside the chamber, we've created two functional zones: the deep water feeding zone at the bottom and the highly oxygenated air gap right above it. Roots suspended in this dual zone environment face zero physical resistance when absorbing water and nutrients. The specific fluid dynamic environment provides perfect frictionless mass transfer, bypassing the severe physical limits of traditional agriculture. A few days after suspending the seedling, we perform the first physical growth check. The visual indicators of biological success are clear. The roots are expansive and bright white, and high turgor pressure keeps the leaves perfectly crisp. Conversely, the indicators of a failure state are obvious. If the roots are turning slimy and brown, accompanied by a foul odor, the system has broken down. The mechanism behind this failure is usually environmental. High temperatures or stagnant water breed anaerobic bacteria that suffocate the entire system. To keep the system running, the ongoing feeding routine is strictly measured. You top up the reservoir with precise nutrients as the water level drops. We are trying to achieve homeostasis, maintaining the exact same water volume, the exact same temperature, and feed ratio every single time. Engineering repeatable homeostasis entirely removes the chaotic drought and drown cycle of traditional dirt gardening. At harvest time, the final state of the plant is a massive, highly structured lettuce canopy, grown entirely in a remarkably small volume of space. The density and cleanliness of this canopy easily surpass a standard dirt-grown plant that spent its life fighting outdoor elements. This split chart reveals the core biological reason for this superior yield: zero wasted metabolic energy. The soil plant loses a huge portion of its energy to physical resistance, while the aeroponic plant directs 100% of its energy to canopy growth. Suspended in an ideal environment, the plant never had to recover from drought stress, search for deeper moisture, or force its way through compacted soil matrices. The physical build itself is brutally efficient. It operates within a microscopic footprint, and the entire setup costs $10. This project successfully reverse engineers a localized aerospace microclimate on a shelf, proving that engineering control is the ultimate catalyst for biological output. Once you stop thinking like a dirt gardener, you start building like an engineer. A simple lettuce system can become a reliable food machine when you control the root zone, manage the air, and keep the feed steady. You do not need a field. You do not need perfect weather. You need a system that works every time you repeat it. Start small, build clean, and let the roots do the rest. And if you want more forgotten builds, hidden history, and backyard engineering like this, just subscribe to Unearth the History.